All right, so the idea here is that we're going to be looking at tests that test for series that aren't easily handled. Like for example, we've seen geometric series; those are pretty easy to handle. You just write a couple of terms, you determine the common ratio, and then you're done, right? And we've also looked at the P series, where all you have to do is look at the power of the n value in the denominator, right? So like 1 over n squared, 1 over n power 3, 4, right? Then we also saw the integral test, right? So what we're going to be looking at here is how to tell whether a series converges or diverges by comparing it to a simpler series, right? So say I gave you like some weird looking complicated series, and you weren't exactly sure if it converges or diverges. So what you do is you take another simpler series, right? And you compare it to that one. So that's the point of the direct comparison test. Okay, so the direct comparison test, I would say the direct comparison test.
Do you have a third board up, or?
I'm not sharing it yet.
No.
Oh, okay. Okay, can you see?
Yeah.
All right, cool. All right, so the direct comparison test allows us to compare a series having complicated terms with a simpler series. Right, so this simpler series, we already know whether it converges or diverges. So we're comparing a complicated series with a simpler series whose convergence or divergence is known. Right, so simpler series whose convergence or divergence is known. Okay, so let's take a look at a more formal definition here. Direct comparison test. All right, so let's say we have a series of terms a sub n and a series of terms b sub n, right? And let's say that a sub n is greater than 0 but less than or equal to b sub n, right, for all n. Right, so a sub n is greater than 0 but less than or equal to b sub n for all n. Okay, so our first conclusion is that if our sum from n is equal to 1 to infinity of b sub n converges, right, so if the sum of this series converges, then the sum from n equals 1 to infinity of a sub n converges. Alright? So if the sum of b sub n converges, then the sum of a sub n also converges. Now again, this makes sense because b sub n is a greater function than a sub n, right? So the summation of b sub n is larger than the sum of a sub n for all values of n. Therefore, if the larger series converges, then the smaller series must converge, right? It's similar to the example I showed you yesterday with the integral test, how the series was bounded above by the integral, right, or the line of the f of x, right? Therefore, since the area underneath that line of that curve was finite, then that means that the series, right, underneath it was also finite. So let's look at number 2. Okay, so for number 2, it says if the sum from n equals 1 to infinity of a sub n diverges, then the sum from n equals 1 to infinity of b sub n diverges. Okay, and this also makes sense because a sub n is a smaller series than b sub n, right? So if that diverges, then definitely the greater series also diverges. All right, so notice that the point here is to make sure that you come up with a secondary series that is, either less than the series you have, right? So you come up with an a sub n that's less than b sub n, or you come up with a b sub n that's greater than a sub n. So you're coming up with smaller or larger series in order to compare to the original series that you have. And the idea is to come to one of these conclusions. So does it make sense so far?
Yeah.
Yeah, so it's a pretty straightforward kind of idea, right? So let me show you how we use it in an actual problem. Okay, so here we're gonna have a sum here. So we have the sum from n is equal to 1 to infinity of 1 over 2 plus 3 to the power of n. Okay, and we want to determine the convergence or divergence of the series. Okay. So the thing is, we have this 1 over 2 plus 3 to the power of n. And we want to check to see if it converges or not, right? Okay. So I want you to, over here, don't copy down anything just yet because it might get a little bit confusing, but I want you to pay close attention to what I'm about to do. Okay, so what we're gonna do is we're gonna come up with a new series, right? And we're gonna come up with a series that we're sure is larger than this series, right? And we're going to show that that series converges, okay? And if that series converges, right, then that means that we've met conclusion 1, right? Because conclusion 1 says if you can come up with a larger series that converges, right? B sub n is bigger, right? So it converges. Or it's not so it converges, but we're going to show that it converges. Then that means the smaller series converges, right? Okay, so we're going to say let a sub n equal 1 over 2 plus 3 to the power of n. Right, so we're letting a sub n equals 1 over 2 plus 3 to the power of n. Now, what we're going to do here is we're going to create a b sub n that's larger than this. And we're going to do that by removing the 2 over here, right? So we're going to make b sub n equal 1 over 3 to the power of n. Alright. So, does that make sense how I came up with this one and it's larger than this?
I see that the 2's gone, but I'm confused why. Like,
Okay.
I get why, so you said that the a sub n is larger than the b sub n, right?
No, the bn is larger than the an. Okay. So yeah, that's why I want you to pay very close attention here, because it might get kind of tricky. Don't copy anything down yet.
Okay.
Pay full attention. So bn is 1 over 3 to the power of n, and an is 1 over 2 plus 3 to the power of n.
Oh,
Right?
okay.
So bn is larger than an because an, you got this extra 2 in the denominator, so the denominator is bigger, right?
Yeah.
Right. So let's say, so we said let an equals this, bn equals this. So we know, we can see that b sub n is greater than a sub n, right? Okay, so far so good. So now we need to show that b sub n converges, okay? We need to show that this guy converges. So we can see that the sum from n equals 1 to infinity of b sub n right, this is 1 over 3 to the power of n. This is a geometric series, right? And what's our common ratio for this one?
Oh, our common ratio, that I was thinking it's supposed to be 3 or
Not 3.
Oh wait, would it be n?
No. So it's geometric with,
Oh, so we use the other test, right?
no. This
Oh,
is a
okay.
geometric series with r equals 1 over 3, right? So again, let me just sort of go back and do this again, right? So we have our series here, our original series. And the goal is to determine the convergence or divergence of the series, right? So we said, okay, let's represent the term in here as a sub n, right? 1 over 2 plus 3 power n. Let's create a new series now that's bigger than this series. It looks similar, but it's bigger, right? And all we did was remove the 2. So now we have 1 over 3 power n. So we know for certain that b sub n is bigger than a sub n for all n, since its denominator is smaller, right?
Yeah.
Say for all n. So now that we've established that, we can also see that the sum of b sub n is a geometric series, right? It's just the sum of a geometric series. The ratio, the common ratio for this geometric series is 1/3. Now, what's our rule for geometric series again when it comes to the common ratio?
I'm mostly thinking about like the formula, like the AR squared, not squared, but like to the
Ye-
power of n.
Yeah, no. You're talking about the a over 1 minus r, what it converges to. Right. Oh, you're talking about this one?
Yeah.
Yeah. The a is 1
Mhm.
and the r is 1/3, right? Because it's like you have a sum of 1/3 to the power of n.
Oh, okay. Because the power of n's there, so
Yeah.
there's one. That's
Mhm.
okay.
Right, so that's where the little n here is coming from. But yeah, so it's geometric. The common ratio is 1/3. Now, what's the rule for geometric series on how they converge?
If it's smaller than one,
Correct,
then
right?
yeah, it converges.
So if the r is smaller than 1, the absolute value of the r is smaller than 1, then it converges, right?
Mm.
So we can say that sum 1/3n converges. Right? It converges because r equals 1/3 is smaller than 1, right?
Mhm.
Okay. So since we know that this bigger series converges, then by conclusion 1 over here, right, the a sub n converges, right? So this original series converges. So this is how we make our conclusion. We'll say since sum b sub n converges, sum a sub n equals the sum of 1/2 plus 3 to the power n also converges. Right, so it converges by comparison. All right? Did that make sense?
Yeah. Yeah, because the b sub n is bigger than the a sub n, so they both
Right.
converge.
Right, exactly, right? So comparison tests are some of the most confusing tests, right? Because first you got to come up with the series that's bigger or smaller, right? Then you got to show, whether it converges or diverges using one of the previous tests, like an integral test or p-series or whatever, right?
Yeah.
Once you've made that conclusion, then you go back and say, okay, since this one is bigger and it converges, then the smaller one converges. Or since this one is smaller and it diverges, then the bigger one diverges, right? You got to make one of these two conclusions, right? So yeah, just take some time to copy this down, and then we'll do a couple more examples.
Okay.
Okay, let's for this one we have say determine the convergence or divergence of the sum from n equals 1 to infinity of 1/2 plus root n by comparison. Right? Okay. So let's see here. Right, so for this one, what can we compare it to in order to figure out whether it converges or diverges?
Wouldn't it be to itself? Like,
Right, so remember, you want to decide a couple of things. Decide on an A sub n and B sub n, right? Determine which is bigger. Which is bigger. And then you just want to compare.
okay. So on the last one, we had 1/3 as the B sub n. And so, in a way, I was kind of confused, like what process we went to get rid of the 2. Was it to like simplify it? Like, I was thinking, like,
No,
yeah,
no, we just created the new function, right?
okay,
We didn't simplify or anything like that. We just chose and created a new function without the 2. And then said, okay, well, this function is not function, but series, right? Created a new series without the 2 and said, well, this one is bigger, right? So let's see if this one converges, and it did. And that proved that the other one converges.
So for this one, can we go with 1/3 plus square root n?
1/3 plus square root n?
Yeah.
We could, right? And would that be a bigger function or a smaller function? Or a bigger series or smaller series?
It'd be a smaller one.
Yeah, it'd be a smaller one. Now, that's fine, but the only problem is that it still looks exactly like that. It's just that you replace the 2 with a 3, right?
Mm-hmm.
So normally the procedure is to remove all the other terms attached to the n.
Okay.
Right? That's sort of what you want to do. Right. So because the idea is you want to rewrite it as a simpler series, right? So the 2 is making it complicated. But if you replace the 2 with a 3, it's still sort of the same level of difficulty. It's just that you've replaced 2 with 3.
Can we get rid of the square root, or is that like part of it?
Almost. You're almost there.
Okay.
Right. What did you have in mind?
Squaring the n.
Okay. So are we leaving the 2 or getting rid of the 2?
Oh, we're also getting rid of the 2 as well.
Okay. So we can go that route. So we can say, now if we do that though, right? Is it going to be a smaller one, or is it going to be a smaller series, or would it be larger?
This one it'd be larger. Yeah.
Okay.
Well, actually, it might be smaller depending on like what number n is for like that square root right there. So
yeah, let's compare, right? Let's do a comparison. Say we just have 1/n, and we had 1/square root of n, right? And let's say n is equal to 100. So over here we get 1/100, but here we got 1/10. So
Yeah.
which one is bigger?
The 1/10.
Yeah, the 1/10, right?
Yeah.
So that's telling us that the 1/square root, that's going to be the bigger function, or keep saying function, the bigger series.
Okay.
Okay, so we've chosen an appropriate, an appropriate series representation, and we know which is bigger. So let's say, since in the theorem that we wrote down, we let b sub n be the bigger one, right? So let's say our a sub n is equal to 1 over n, and our b sub n is equal to the 1 over square root, right? That's the one that we have. Well, not we have, but let me write it the way that we have here. 1 over 2 plus square root of n, right? All right, so the a sub n is smaller. So we'll say our a sub n is smaller than b sub n. Okay, so we've chosen an, we've chosen bn. We know that an is smaller. Now the question is, does the an converge? Or does it diverge?
So we do this by using the test, right?
Let's see. Right, because when we're comparing our original to this new one that we just created.
Mm-hmm.
Right, so now we want to know if this one converges or diverges.
Oh, so are we gonna do that through the test? Maybe not like the geometric one, but like the other one. I forgot what name it was. It was the one where it's like not equals 0.
Not equals 0.
Let me find it.
I think I know what you mean.
I believe P series.
Right, correct. So we're gonna say we can apply P series here, right? So according to P series, does this series converge?
According to P series. Okay.
So P series, it says series of the form sum of 1 divided by n to the power of p, right? And in the red box, it says the P series converges for p greater than 1 and diverges for p between 0 and 1.
Yeah.
Right? So we can use P series to make a conclusion here.
Yeah. Series form. So for P equals 1. So would I make just a regular series where it's like P of n of 1, then n of 2, then n of 3?
Let me see.
With the power of P, I believe.
No, you just have to check the power. Right? It's just the power. Right? So this is power of 1. So we'll say this diverges because P is equal to 1. So we'll say this is divergent by P series. Since P equals 1. Right? Also, this is the harmonic series, right? Sum of 1 over n is harmonic. Is the harmonic series, which diverges. So now we know that this series diverges. And what we want to do is we want to compare it to, we want to make a conclusion based on the comparison test. So the comparison test says that if we compare a smaller series to a larger series, and the smaller series diverges, then the larger series also diverges. Right? That's the conclusion we wrote for the direct comparison test. So we'll say since since a sub n is less than b sub n for all n, and sum of a sub n is equal to sum of 1 over n diverges, then the sum from n equals 1 to infinity of 1 over 2 plus radical n also diverges. So now let's look at let's take a look at the limit comparison test, right? So the last comparison test we did was direct comparison, which means you create another series to compare it to the one you have. Okay, so for this one, what we're doing is we're trying to take a limit, right? We're using limits to help us out. And the way it goes is like this. So say, for example, you have an a sub n that's bigger than 0 and a b sub n that's bigger than 0. Right? And then when you take the limit as n goes to infinity of a sub n over b sub n, you get some finite value L. Right? So L is finite and positive. Okay, so you take the limit of the ratio of a sub n to b sub n and you get a finite value L. Right, so L it has to be positive. If that's the case, then either both series converge or both diverge. So then either first case is that both sum from n equals 1 to infinity of a sub n and the sum from n equals 1 to infinity of b sub n converge, or both the sums diverge. Okay, so when you take the limit of the two series and it equals some finite positive value L, then either both series converge or both of them diverge.
So is it supposed to be the inverse of the direct comparison test?
No, it's just another way of looking at it. It's a perspective of looking at it by taking limits.
Okay.
Right, so the direct comparison test, you're actually comparing it. You're taking this one too, you are kind of comparing it to another series, but you're taking the ratio between the terms and you're taking that limit to as n goes to infinity.
Okay.
All right, so let's determine the convergence or divergence of the sum from n equals 1 to infinity of the square root of n over n squared plus 1. Okay. So we want to determine whether this series converges or diverges. Okay, and the way we're going to do that is first we're going to come up with a new series, right, with a b sub n value, and we're going to take the ratio between a sub n and b sub n and take the limit. Okay, but the thing is, remember what the conclusion says, right? The conclusion says that either both are convergent or both are divergent. Okay, so we know that this series is positive, so we need another series that we can compare it to that's also positive. So we can come up with, let's say, choose b sub n equals radical n over n squared, which is equal to 1 over n to the power 3/2. So it's basically just, I chose this very same series, but without the plus 1. Right, so you want to usually use like a set of terms that looks identical, right? So the only difference between these two is that this one has the extra plus 1 in the denominator. So the next step we want to do is take the ratio. You want to take the ratio an over bn, right? So in our case, our an is this one. So we're going to say an over bn is equal to radical n over n squared plus 1 multiplied by, we're doing an over bn, so it's going to be multiplied by n to the power of 3 over 2. Or, hold on, sorry. Yeah, this looks good. Okay, yeah, because the bn was 1 over this. So if we divide it, it comes to the numerator like this. Okay, so let's simplify this. So we got n to the power of 1/2 plus n to the power of 3/2, or times n to the power of 3/2. That gives us n to the power of 4 over 2, which is just n squared. Right, so this is n squared over n squared plus 1. Now we want to take the limit. Right, so we want to take the limit as n goes to infinity over an over bn. Okay, so we can do that here. Right, and this limit just comes out to be 1. Okay. So, based on the rules we wrote, since the limit is finite and positive, right, that means either both converge or both diverge. Now remember, the original bn was this one over here, right? So we can conclude that since b sub n equals 1 over n to the power of 3 over 2, and the sum of 1 over n to the power of 3 halves converges by p-series, then the sum from n equals 1 to infinity of radical n over n squared plus 1 also converges. So for the limit comparison test, right, you still have to choose some function b sub n, right?
Mhm.
Now, again, you see how we're dealing with kind of a complicated looking series here. So we chose a simpler series to deal with. And this simpler series factors, well, not factors, but simplifies to become 1 over n to the power of 3 halves. Now, after that, we just take our ratio, the an divided by bn, which gives us this result. We take the limit of that as n goes to infinity. That gives us this result, right? Which is finite and positive. So that means that either both series converge or both diverge, right? But we already know that b sub n must converge because of p-series, right? So since b sub n converges, right, because of p-series, that means that the a sub n also converges. Right? So that's the idea behind limit comparison test. It tells you whether both functions, both series converge or diverge, and if you already know that one of them converges, then that means both of them converge. Okay, so in this example, we have the sum from n is equal to 1 to infinity of n times 2 to the power of n divided by 4n power 3 plus 1. You want to know if this converges or not.
Okay, so we're using the comparison test, the limit one for this.
The limit comparison test.
So in this one, we're trying to make it's like the other one, right? Where we're trying to kind of like make a separate, not a separate, but like basically a BN or an AN to look at,
Yeah.
right? Okay.
Yeah, we want to choose a BN that looks similar to this, right? Because we're going to eventually take the ratio.
Okay. So I guess we can have n times 2 to the power n divided by 4 times n cubed without the 1.
Okay. All right, cool. So let's check that one out. Okay, so we've chosen our BN.
Mm.
All right. Okay, so our next step.
Decide which one's probably smaller, and I believe that would be the
Well, remember, limit comparison test doesn't doesn't involve which is smaller or which is bigger. That's direct comparison test.
Oh, okay. All right. So, okay, so we're taking the ratio of AN. Okay.
Okay, so we're gonna take
the original one times the new one.
Right.
Okay.
So we're taking the ratio. So this will be 4n cubed over n times 2 to the power of n. Are we able to simplify anything?
The can we like cross like the n times 2n?
Alright, so these two cancel.
Same with the 4n cubed.
No, because this is being added to 1.
Oh, okay. Okay. So new ratio would be 4n cubed divided by 4n cubed plus 1.
Okay. Alright, so what would be our next step?
To take the limit of our new ratio.
Alright, so we're going to take the limit as n goes to infinity. 4n cubed over 4n cubed plus 1. And what do we get here?
So we're taking it to infinity. So it would be infinity over infinity, right?
No, that's indeterminate.
Oh, well, that would we get that out of this, like an indeterminate number?
No, because we have a polynomial over another polynomial.
Oh, okay. So, all right, that makes sense. Oh, so we take the ratio of those two, right?
Right, so we take the ratio of the leading coefficients. It's 4 over 4 is equal to 1.
Okay.
Right, so our limit is positive, finite, which means that either both the series that we created converge or both of them diverge.
Yeah.
Okay? Okay, so what's our next step here?
So to, I guess, explain everything. So since B sub n converges, then our A sub n also converges. So our B sub n being n times 2 to the power n divided by 4n cubed, and our A sub n being our n times 2 to the power n divided by 4n cubed plus 1.
Well, we don't know if this converges yet.
Oh,
Okay, how do you know this converges?
I was just like basing that off of like how we took the ratio of both of them and we got like a finite number of that.
Well, that's fine, but the finite number only tells you that either both converge or both diverge. You don't know which one.
Okay.
So, since you don't know which one, you need to check to see if the B sub n you chose converges or diverges.
Okay. So we're gonna check using one of the series tests, right?
Yeah, this one we could. So let's write this. B sub n is equal to 2 to the power of n over 4 n squared. What we can do is we can use the divergence test, though. We could use the divergence test. So we'll say apply divergence test. So if we take the limit as n goes to infinity of 2 to the power of n over 4n squared, right? What's going to happen is that this is an exponential function where you have a power function down here. So exponential functions grow faster than power functions. So this limit would be infinity. Okay, so remember the divergence test that if your limit, it says that if your limit is non-zero, right, then automatically your series diverges.
Yeah.
Right, so we'll say sum of 2 to the power of n over 4n squared from n equals 1 to infinity diverges. Alright, so now that we know that b sub n diverges, we can say therefore a sub n also diverges. So we'll say since b sub n diverges by the nth term divergence test, a sub n also diverges. Alright, because both series do the same thing according to the limit comparison test. So I should say, shouldn't say b sub n, I should say sum of b sub n. Okay, so that's how it works. Alright, that's how it works. So, do you have any questions about the two tests we covered?
So with the direct tests, that's specifically so the situations we would see direct tests and limit tests. Is one with like the infinite summation sign and the other without it?
Like how do you mean? Infinite summation sign and other without it?
Like I believe like I forgot like what the sign with the E and the infinity on top and the N equals on the bottom was called, but like I just remember the definition including like infinite summation.
Yeah, infinite summation. But you said another one without it. Like how do you mean?
Yeah, so like would direct not substitution, direct comparison be in problems that don't have that?
Oh, okay, I see what you mean. No, all the problems they're gonna give you, you'll just have a summation, an infinite summation.
Okay.
Like, are you talking about like it wouldn't have it, as in it would just write bn or an like that, or?
Kinda. I'm just mostly like asking for the general like scenarios in which I don't know which I'll be using.
Right. No, they're all, because the thing is, they're usually not gonna tell you. Sometimes they will. Sometimes they'll say use comparison test to determine if this series converges, or use the limit comparison test to determine. Right. So the question might state it out and say, okay, use this test, right? So yeah, that'll definitely show up. But if it doesn't show up, they'll just ask you to use the appropriate test, right? So it'll be up to you. And sometimes certain series can be solved using more than one test. So you can choose whichever one works or whichever one's best for you. And other times, you'll have to try out a few, right? Because some of these tests, they might not yield anything. Like it might be inconclusive, or you don't know exactly. So you might have to try another test that'll work. But with the direct comparison and the limit comparison test, right, for the most part, you know that you have to use those tests when the series looks kind of complicated, right? So it looks kind of complicated, so you want to choose a simpler version of the series and compare it with that. Right? That's the whole point behind the direct comparison test. Same idea with the limit comparison test, right? You choose a simpler version of the series, but this time you're just taking a ratio and taking the limit of that ratio.
Okay. Cool.
Right. Now, let me see. Yeah. So, like I said, this section is not very short. It's just these two tests. The next stuff to cover is alternating series.
Okay.
All right. So, alternating series. There's another test that has to do with alternating series called the alternating series test, right? So this test is useful because now it allows us to, to conclude that a series actually converges when you take its limit. Like if you do limit as a sub n goes to, as n goes to infinity for a sub n, right? If that limit equals 0, now the alternating test tells you that, okay, then it's convergent, right? So essentially what I'm saying is if a series is an alternating series, then try taking its limit as n goes to 0. As n goes to infinity, right? If that limit is 0, then it converges.
Okay.
Right, so that's the we'll get into that one, and it'll become clearer once I explain it a little bit more. So the like I said, the 9.1 and 9.2 are up on the drive, and I'm also about to upload because I forgot to upload the 9.3. 9.3 is for integral test and P series. So once those go up, you can do a couple of practice problems in that. And I also put up today's stuff as well. All right, man. So take it easy. Enjoy the rest of your weekend. And hopefully by next week, we'll be finished with chapter 9.
All right.
All right, cool.
Have a nice
Have a good one. You too. Bye.
Bye.